Please grab your drinks, come and sit down. All right, let's get going with tonight's Cloud Native London. So welcome everybody to Cloud Native London. We are a strong, open, diverse developer community around cloud, data, and AI based in London. My clicker's not doing its thing. Not to worry, we are going to do it this way. So, my name is Cheryl. I am your host for tonight. Our agenda for the evening, we have 3 talks. The first one at 6:45 is Predictable Systems in an Unpredictable World. Our second talk at 7:15 is Observability with HAProxy, detecting what is not working and why. At 7:45, we're going to take a break. Please feel free to wander around, go to the restrooms, but stay in this area. At 8 o'clock, we'll have eBPF, Revolutionizing Cloud Native Security. And then we will wrap up at 8:30 and make our way out and probably find a pub somewhere around here to keep chatting. Our sponsors for tonight. So Aerospike and HAProxy are both doing their company introductions as part of their talks. But of course, I want to say thank you to them for making this event possible. Thought Machine, who is our venue host for this evening, I would like to welcome Glenn to just introduce and say a word or two.
Thanks, Cheryl. Hi, nice to meet you all. I'm Glenn. I'm part of the recruitment team here at Thought Machine. Just wanted to give you a bit of an intro onto us. If anyone's looking for a new role or is interested, we've got a table set over in the corner if you want to come and have a chat to us afterwards or during the break or anything. But little intro, we're a cloud native, hence why we're sponsoring the event. Microservice architectured core banking platform. We basically allow banks and other fintechs to transition a lot of their technology from outdated legacy infrastructure and onto more cloud-based modern infrastructure. So if that sounds of interest to you, like I say, come over and have a chat. We have roles available across engineering. We've got back-end engineers, full-stack engineers, SREs, cloud support, infra engineers, pretty much you name it, we've probably got it. So yeah, we're very friendly, so come and have a chat. Thanks.
Thank you. And then Tech Shack, I will do a shout out for. So Tech Shack are a tech recruitment agency specializing in the cloud, engineering, and AI. Tech Shack exists to build high-performing tech teams by putting community, connection, and quality first. So thank you very much again to all of our sponsors who, without them, we wouldn't be able to have these wonderful events. And now I want to learn a little bit about you. So please grab your phones, scan this QR code. I'm going to do a bit of live polling for the audience. You don't need to sign up for anything. You don't need to give your name. It's just some questions about you and then some questions from our speakers. Okay. First question, is this your first time at Cloud Native London? You should just see yes or no. And I see people already voting. The results are coming in. Looks like the yeses are pulling ahead. Oh, we're pretty much 50-50 tonight. Let's give people another moment to figure it out. Are the no's going to put it back? We do have people, we're live streaming to YouTube and to LinkedIn. So there might also be people at home voting with us. Oh, end it on 50-50. Come on. Okay, wonderful. What's your job title? So pick whatever's closest to what you do. Architect, application developer, backend developer, engineering manager, DevOps/platform engineer, security, or anything else. And the anything else is coming out strong tonight. It's almost 60%, 55% of the crowd saying anything else. So please do and come and introduce yourself to others and sort of tell people what you do. Okay, your database reports a 75% cache hit rate. Would that by itself improve P99 latency? This is a bit of a trivia question for you. Yes, no, or only if there's a throughput bottleneck without a cache. You cannot Google it. You cannot ChatGPT it. You cannot all the others either. Wow, so what are we thinking? Oh, it's even yes, no, that means nobody knows, right? Nobody knows. And 14% of people are saying the complicated answer sounds like the right one, so I'll choose that. Where is, Dan, so you submitted this question, so tell us, will it improve latency?
Always the longer answer is the correct answer. It's always, there's nobody has time to just generate wrong answer that is that long. So yeah, last one is correct.
Very good. Okay, I look forward to hearing a little bit more about this. No, you cannot change your answers now, whoever just voted. It's too late. Okay, next question. How do you currently visualize your load balancer metrics? So we grep raw logs. We send metrics to Prometheus/Grafana. We use an Elk/Splunk stack. We don't really look at metrics unless something breaks. And what's a load balancer? Give people a moment to vote. And where is Baptiste? Yes. So what are we saying? 40% of people do not know what a load balancer is. Is that what you expected for this question?
Yeah, that's why I introduced a few slides to educate you on load balancer and reverse proxy and things like that. So you will have some answers.
Okay, fantastic. Nice, the 5% of people just grepping raw logs, living life on the edge. Last question. How would you describe your organization's current cloud-native security visibility? So are you flying blind? So we have gaps, we know containers are running, but not really what's happening inside them. We monitor the perimeter, but we don't have runtime. With me. So before we go into, usually at this point, I would go into the talks. I just have a few more things that I want to talk to you about. Okay, so I want to talk to you a little bit about the future of this meetup, Cloud Native London. And in fact, I want to start by just going backwards a little bit in time. So I started this meetup in 2017, July 2017. As a developer advocate, I was going out to speak at lots of events myself, and I was looking on meetup.com, and I saw there was a Cloud Native Berlin and a Cloud Native Paris, and there wasn't a Cloud Native London at the time. So I just kind of threw it up on meetup.com and hoped that, people would show up, and kind of scrambled for about 7 weeks to get speakers and get a venue. We ended up at the Sainsbury's headquarters and everything else. And at the first meetup, more than 100 people showed up. So I was like, cool, okay, this is great. There's clearly demand for this. 2020 hit, obviously, pandemic, and this became a virtual event for 2 years. That was a slog, let's say. It was really hard because I'm a person who loves live events and loves being with people and loves seeing people face to face. So for 2 years, it was like grinding to keep this going as a live event. Like I had this little tool where people could watch and, kind of interact online, but it was really, really tough. Come 2023, we kind of came back and I was so happy to have live events again. We celebrated Kubernetes' 10th birthday party as well. And then just a few months ago, we hit the 100th meetup, and we also hit 10,000 members for the meetup. So that put me into the mode of thinking, like, what else would this community like to see? What are more things that I could do to be more useful and to do even more? A lot of the kind of peer meetups like Docker London and Kubernetes London are no longer around because after the pandemic, they didn't come back. But I thought this would be a good opportunity for me to ask you a little bit about what would be fun? What would you enjoy seeing? So this is the same poll that you've got on from before. If you didn't have it, I want to ask you, where do you think we should go next? Okay, so here are some options for what you might be interested in or your company might be interested in. So we could do an annual conference. We could do trainings and workshops, for example, for the certifications, a job board, because I know a lot of people are looking for roles right now. Do a newsletter, a podcast, do some kind of sponsored content online, or do some vendor market research, because people tell me, hey, we want to hear what the community really thinks about our new tools or about these tech trends. Give people a moment to think about this. So training and workshops and job boards seem to be the top. Okay, awesome, thank you. And then I have some slightly more like experimental ideas here. So I could start another meetup around AI and ML because everybody else is. Could do a London tech scene report about like who's hiring, what are the salaries, what are the tech trends, tooling trends. Do a CTO retreat, get some other high-level technical people together and just go like disappear for a weekend and do something fun. Founder and engineer matchmaking. So if you're a startup or you're interested in working for startups, then match those. Or kids/teens coding day. Okay, so AI/ML meetup or a report about the London tech scene. Okay, awesome. Thank you for your opinions. As part of this, I'm creating an advisory board because I want people who are interested in volunteering a little bit of time every month and want to give their opinions and talk to me about it. So if you want to go and make the London tech scene, the tech community even better, do even more, welcome more people in, then this QR code just sends you to a thing where you can put your email in. It's not committing to anything right now. It's just like, oh, I'm interested in representing my interests, my organizations. This could be anything, right? Like if you are a recruiter, recruiters are great. If you're a student, students are great. Like vendors, I really want to make this a place where everybody feels like they're welcome and there's something for them. And also, of course, just come and hang out with other people, other cool people who like to do community stuff. And I will figure this out over the next coming months. All right, awesome. Okay, that is it for me. So now I'm going to hand over to our first speaker. Please welcome Behrad.
How's everybody doing? Cool. So I wanted to start with a question. Who is old enough to remember dot-com bubble? You don't look old. Yeah. Okay. Well, I lived through dot-com bubble, but I wasn't old enough to remember the financial difficulties of it. But I was a tech-savvy teenager, so I was using internet back in the 1996, 7, 8. And I remember the dot-com bubble. Something that was very interesting was that people were seeing that this revolutionizing technology is coming to the market, and everybody had an idea, and they wanted to basically implement their ideas and do something incredibly interesting. But some of the things that were happening were just so daft. It's just like incredibly crazy. So somebody was just thinking that, oh, pizza is something that is very interesting. So I should go and register pizza.com. And then I put a picture of pizza in the first page, and I just write a bunch of text saying that I'm going to do pizza here. And then, well, it was always middle aligned as well. Everything was in the middle, nothing on the side. And then it was saying that, okay, this is going to be my company. And then people were just spending millions of dollars, literally millions of dollars on this idea. So it was something absolutely daft, but people were happy to part their money to invest on these ideas because they were thinking that registering a domain is something absolutely amazing. But then, lots of other interesting things happened as well with the advent of the internet. So one of the most important one was that we very quickly learned that no single machine can handle the scale of the internet. So, before that, there were companies that had to use distributed systems to build their systems. But it wasn't a common thing. Not everybody has to do that. It was a niche thing to do distributed computing. But after the internet, like everybody had to think about how we can distribute our workload across lots of different machines. And, well, we had to become really good in that. We first started creating these distributed systems. Then we had to learn how to scale these distributed systems. Basically, if you start with like 2 servers that are doing that thing and you are successful, how can you make that 2-fold? Is it going to be simple? Is it going to be complicated? And then when we started having lots of components in the system, there was a possibility of failure. The failure of each individual system started to increase. So we started focusing on availability. So how can you build something that if one of the components fails, the system is going to continue? So yeah, there was something rather trivial happening at the time, registering a domain like pizza.com, but there was something also fundamental happening underneath. So that has a bit of parallel to what is happening right now with the advent of AI. Well, not advent of AI, advent of generative AI, the new generation of machine learning and artificial intelligence that we are facing today. So a bit of it is a hype, which is, I don't know, maybe in 10 years, we are looking at a bunch of these things that are happening in the market, and we think that, oh, it's like registering pizza.com. I mean, companies that are just like built on the idea of calling a bunch of APIs from, one of the LLMs and, just passing through the result. Maybe in 10 years, we look at them and that idea seems as trivial as registering a domain. But nevertheless, there is something fundamental happening underneath, which is, beyond this hype about the LLMs and all of the things that are happening. And in this talk, I'm going to focus on that. I'm going to say that, okay, what is this seismic change that is going to happen, which is similar to the distributed systems or scalable systems that started to become standard. And basically, I don't think that anyone today is building an application that is not supposed to be scalable and available. What is that thing that is going to happen now that is going to become standard in like 10 to 15 years from now? So to be able to do that, you either have to have a crystal ball to predict the future, or you should look at what is happening right now and try to guess what is that thing that is probably going to happen in the future. So I think the best way to describe it is to look at what we had yesterday and how it is changing for the applications that we are building today. So what we had before was that if you were building an application, let's say it's a website and you want to load a web page. So when you want to load this web page, you probably connect to a service, and that service calls a bunch of microservices, probably 2 or 3. One of them is logging you in. One of them is, I don't know, giving you entitlements, and the other one is giving you the content, right? And each of these microservices, I don't know, probably some of them might talking to other microservices. Some of them might call something read something from a database. But this graph of dependency is relatively small. You probably need to make like 5-10 calls to get all of the information to show it on a web page. That's one of the characteristics of the things that we were doing before AI. And the other one was that it is somewhat deterministic. So you might have some if-else statement that says that if you have this information, don't read it from the database and, I don't know, read it from the cache or something like that, that is changing the number of requests that you are doing, but it is still deterministic, right? You can still read the code and say that, yeah, if I run this thing, it is going to generate these many calls on my underlying systems. But this is going to change with generative AI applications. So let's focus on agentic AI because that's the extreme of it, and the extreme of it shows what is going to happen. So I might have an agent that is going to book me a trip to Tokyo, right? And I don't know, I write a query, I say that, yeah, book me a trip to Tokyo in April this year. So this agent is probably have to look at my calendar, figure out which time in April is a good time for me to travel, have to check the airlines, figure out that which week is going to be cheaper, which time is going to be more suitable for me, probably has to look at the hotels, look at the past conversations that I have had with that LLM and figure out what kind of hotels are likely to be good for my taste. It probably has to figure out what kind of food I like, find the restaurants that I'm interested in, and then find the distance between those restaurants and the hotel that is going to recommend me. So, I mean, you see, it can become increasingly complicated. So just one interaction that I made with this system has 2 characteristics that are new. One of them is that this basically fan out, I call it is being fanned out. You see that in that picture, that it is fanning out. This fan out is going to be very, very large in comparison to what we have today. And the second thing is that this fan out is unpredictable, because if I do that query once again, 5 minutes later, that agent might do something slightly different. Or if you are doing it based on the conversation that you have had with your LLM in the past, that LLM might decide that, oh, you're a guy that prefers to, I don't know, stay in an Airbnb, so I should go to Airbnb instead of a hotel. or you're a gal who's interested in living in a, I don't know, staying in a luxury hotel. So I have to start looking on that specific one. So that same query is going to be completely undeterministic, where it's going to go, how it is going to be executed. So these are the two main differences, and I'm going to discuss that, what these two differences are going to force us to do. So first, before going to the two important ones, well, it's obvious that the scale is going to increase, right? We said, one human interaction used to generate, let's say, 10 database calls, 10 tool calls, or whatever. So that is becoming like 100 or thousands. But the good thing is that, as we discussed during .com bubble, we learn how to scale our system. So that's something that we are good at. We can already scale our system, create systems that can handle 10 times more load. So we don't have any problem with that. But there are two other problems that we need to discuss. So first one is related to the sensitivity to variance. So remember, we said that one request comes in. Before, it was 10 sub requests. Now one request comes in, there are 100 or thousands of sub requests. When you have many sub requests, you start to become more exposed to the variance at the tail. Let me explain what I mean by that. So let's say you have a database that 99% of the times perform at 10 millisecond latency, right? So 99% of the time, your response is 10 milliseconds. And then 1% of the times, it is slower than 10 milliseconds. So if you have a service that needs to make 100 data lookup to get all of the data that is required for that service to complete its task, the possibility that every single one of those 100 requests that you are sending to the database is 99% to the power of 100, because it's a smaller number than 1. When you make it to the power of 100, that number is going to become smaller. That number actually gets down to 37%. So if you have a database that 99% of the time is performing at 10 milliseconds, there's a 37% chance that all of the requests that your system needs to make are going to be completed in less than 10 milliseconds. I'm assuming that you're sending everything in parallel. If you're not doing that, you have to do it in parallel, but that's a different story. So if you do that, so it's going to be like that. So that's something to have in mind. But now you might say that, okay, 10 milliseconds is not too bad. And I mean, it might take 11 milliseconds. Why should I care? So the thing is that when you are looking at distribution of latency, the distribution of response time, you have this long tail that as you become more rare, the operation is taking longer, right? So you might say that, yeah, at 99%, it is 10 milliseconds. But what about 99.9%? At 99.9%, the latency might be around 100 milliseconds. So now if 99.9% to the power of 100 is calculated, the result would be 90%. So in this situation, 90% of the operations, the data part of it, is going to be completed in 100 milliseconds, which is good. It's just 10%. But of course, there are some events that might be happening that are taking then more than 100 milliseconds. I don't know, there might be it's very rare. It's 1 in every 10,000, but your router might drop a packet. Maybe there's a noise on the link, and the link is not really delivering the message. I mean, Alam is going to talk about network, so listen to him. He's going to explain why these things are happening. No, he doesn't. So if you have a 99.99% possibility of not hitting that bad situation, still, when you put it to power of 100, that power of 100 brings you to 1%. So still, just for like 100 requests, your users are going to notice the latency of the rarest thing that might happen in your system, right? So the things that today we don't care about, we keep them as a statistically insignificant events, are going to surface in your application. So, and that is like basically the logic of it. You know, as you are doing more and more requests, your single interaction with the system requires more and more interaction with the database. You are going to be exposed more and more to these tail events. So that is one of the things that is going to change. So the other one is that you cannot really optimize anything anymore. So optimization is something that we do to reallocate resources to part of the problem that is more often. More often is assuming that there's a steady state. There's a, let's say, I mean, when we say optimization, a typical optimization approach is caching, right? You put a cache in front of your slow system and you try to make it faster. So the idea of caching is that I put 5% of my data in RAM, right? But this 5% is going to answer 90% of the requests. So it's a win, because that although I'm using all of my RAM to keep this tiny amount of data in RAM, but because 90% of the requests require that 5%, I'm going to make my application faster. But as we discussed, that graph that is that execution graph that was being created by the agent is so random that you don't have a steady state. So that steady state, because it's not there, you cannot really optimize your solution, right? So this is the second thing that is going to change. So to talk about it again, so you have this AI that is fanning out. So you have an AI with a massive fan out. Because of that fan out, you are going to be exposed to the tail latency, and to be able to handle that, you require a system that has a relatively tight bound variance at the tail of its performance characteristic. So we can basically conclude from this that the applications that we need to build in the future are going to become more deterministic. So we build our applications in the past to become more scalable. That became the thing that we wanted to do. That was the characteristic that we spent so much time to master. I mean, scalability was the first version, then I don't know. Everything that we did with service-oriented architecture was about the scalability. Then service-oriented architecture didn't really work. We switched to microservices. That was about the scalability. Kubernetes is about the scalability. Then I don't know. Now we have elastic services. Elastic services are kind of a stability, are kind of a scalability. So that was the thing that we were focusing because of the internet. That is going to stay. That is not going to go away. That is something that we did to something that we mastered and is going to continue staying with us. But that is not going to be the differentiator anymore. We have to focus on building these deterministic systems. So you might be asking that, okay, who are you to tell us that this is true and we can actually build deterministic systems? And that's a very good question. So the thing here is that there are actually applications today that require that kind of characteristic. You know, and as I was telling you the story of dot-com bubble, I told you that in the past, you know, before even internet, there were companies that were building distributed system, that it was kind of a niche. Right? Like then, there are applications today that have that fan-out problem. And those applications already have that problem, and they have to fix it. So the type of applications that we are talking about are, that's a little bit too early. So the type of the applications we are talking about are like fraud detection. So if you think about fraud detection, so at the point that you go to a point of sale and you touch your card, the bank has to do lots of database calls to get probably the past 100, 200 transactions that you made using that card, and also all the other accounts that you have. Look at all of the vendors that you purchased something from, what time of day you purchased them, what amount of money do you usually spend. So they fetch all of this data, and then they put them in a machine learning model, and the machine learning model give them a risk number, and based on that risk number, they decide to either say that it is a fraudulent activity or it is not a fraudulent activity. So if you are building a fraud detection system, you already have that what is it called? The fan-out problem. So the fan-out problem is not something that is going to just appear out of thin air. That problem already exists in a category of applications that are being built today, but now it is just going to move from being a niche to some specific problems to almost everything that we are going to do, because everything that we are doing is just going to become more and more complicated, right? So luckily, I work for this company called Aerospike that has a database that was built to be deterministic. So we have a very tight tail latency, right? So when you're comparing our P99 with P999 with 9,999, this number is not exponentially increasing. It is a reasonable increase, and that's this. For that reason, I'm saying that it is a bound thing. And we are very common in fraud detection systems. Very, very common in fraud detection systems. It's not only fraud detection. If you are in prediction, if you are in recommendation engines, if you are in what else? Feature stores. If you are in this kind of use cases, our technology is very, very common because of this very specific reason that I described. I can give you some names. For example, if you are a customer of Barclays is a customer of us. The fraud detection systems run on Aerospike. So when you touch your card, they are usually doing around 500 to 700 transactions on their database to fetch the data that is related to you, to put into their data model to figure out if this transaction fraudulent or not. Another very famous customer of us there is PayPal. PayPal is also their fraud detection is based on Aerospike. Again, whenever you are pressing a purchase, they are on average doing around 1,200 database calls to figure out if this transaction is fraudulent or not. So this is a very common thing. If you have a fan-out problem, you need a database that has this deterministic behavior. But, well, one of the things that we need to do to create a system that is not that is deterministic was that to remove the sources of having unpredictable response. One of them is a caching layer. We discussed the caching layer. If you hit the cache is going to respond very, very quickly, and it is going to be very, very fast. But if you don't hit the cache, it is going to go to the disk. Unless 100% of the requests that are on the cache, you are generating that long tail latency. So we didn't want to have that. So we built the system without a caching layer. And you might think that, okay, you build something without a caching layer, so it is now going to be ridiculously slow. So what's the point? But here's the thing. Because we knew from the ground up we have this problem, we didn't think like the other databases, and we built our system without a cache and tried to use other techniques to make the database as fast as possible. And I don't know if you are database experts, but there's a database that is very famous for its performance called ScyllaDB. Has anybody heard of ScyllaDB? Yeah. We did a performance test against them. It was quite shocking for us as well that the result is so one-sided. So if you look at the top two results, so this is for 6 terabytes of data. So first thing that I have to mention is that where's Aerospike? Aerospike is this red line that is in the bottom, right? You probably cannot see it because it's just so close to zero. It's just the amount of time that it takes. But that is not important. That wasn't the thing that we were trying to build. The thing that we were trying to build, and we succeed, is this flat line. We have a flat line latency. When you compare that with ScyllaDB, you can see that ScyllaDB is going up and down. And when you are here at your P99, your users are going to immediately notice this. But we are here. So your user are not going to see any of that. And then when you take it to P999, basically 99.9%, you can see that, well, they are kind of similar, but the numbers are different. So this is peak at 80. This is peak at around 210. Aerospike is around less than a millisecond. Here is less than 2 milliseconds, right? So the performance is not fluctuating. And when you go to the lower percentiles, when you are going to 99.999% of the request, the database is still fast. But also, as I said, as we don't have a caching layer, when you introduce a cache, and I mean, when you say introduce a cache, the system either has a cache or it doesn't have a cache. You cannot introduce a cache. You introduce a workload that can use a cache, and a workload that focuses on a small part of the data. So if you start doing that, when you compare Aerospike without a cache and with a cache, you see that there's no difference between Aerospike in these two scenarios. But in ScyllaDB, the performance becomes significantly better. The performance is actually coming down around 50%. It's become 50% faster. So yeah, cache does something, but this is actually quite a scary thing, because now you don't have any control on the cache, because if users start to do something else, if there's a pandemic and people are buying toilet papers left and right instead of the things that they used to buy, your cache is going to be unpopulated, and then everything is going to work very, very differently to how it used to work for. So, but this is, as we were saying, this is a thing that is going to become more prominent with the advent of the AI. So last thing is that, yeah, we had one great shift with the advent of the internet, which was introduced because of scalability. So we tried to build these scalable systems, but the prediction is that because of the things that we discussed, it's the predictability that is going to become the feature that everybody's going to look for. So that was it. But before that, we have a raffle for that Game Boy. So please enter, but there's a catch. There's actually a survey in the thing as well, and you don't have to fill in the survey, but I would be very, very thankful if you can do the survey. It is for research that I'm doing. I just want to understand that if the thing that I discussed resonate with you all or not. So if you can just pick up your phone and enter and do the raffle and also the survey, I'd be very, very thankful. Thank you very much.
Real Game Boy, is it? It's a Lego Game Boy.
It is a Game Boy, but no, it's a Lego.
This is a Lego Game Boy. I was quite excited for a moment. Okay, wait. We have 2 more minutes for talks. So, question. Were the ScyllaDB and Aerospike benchmarks using like-for-like hardware?
Thank you very much for that question. It's actually a very good one. So actually, no, and you might be thinking that, then why did you do that? So Aerospike actually requires less hardware than other database technologies. And I mean, it might be a little bit crazy, but if you think about it, when something becomes significantly faster, the only way that it can happen is that by using fewer resources, by using fewer CPU cycles, by using fewer disk accesses, by using fewer memory accesses. The only way that you can make something 10 times faster is by using fewer resources. So we actually use fewer amount of resources. If you look at our benchmark, the benchmark has, you can see that the benchmark uses 33% less resources for Aerospike in comparison to ScyllaDB. So ScyllaDB is running on 6 nodes, Aerospike is running on 4 nodes. And that was the result. And then the throughput is also very different. Aerospike throughput is around 2.5 times more than ScyllaDB. So during that performance, when you are seeing that very flat line, Aerospike is on 33% fewer hardware, and it is doing 2.5 times more throughput and providing around 10 times better latency. So that was a very good question. Thank you very much.
Okay. I think that is it for questions. So one more round of applause, please. And please welcome Baptiste. Thank you.
Can you hear me? Ah, that's working. Thank you. Yep. So during the survey, we had a quick question about do you know load balancers or something like that? And I think 40% of people said they have no clue, which is surprising because when you speak about scalability, cloud, anything modern which need to scale, you need something which allows scaling, basically, and that's the load balancer. So I'm director of product. I'm working for HAProxy Technologies. So if you know HAProxy, it's an open source software which is available for 25 years now as a software and as open source. We are the company behind the software, so we are developing the community edition and also an enterprise edition that I will quickly introduce also at some point. We have some swag, so we have some t-shirts. If you find the talk nice and the t-shirts are good looking, pick them up. Okay, so we are going to speak about observability and around also load balancers on this topic. So first, I guess everybody knows what observability is, but just a quick reminder, I just pick up the definition from Wikipedia because I'm lazy, but I could have asked Claude or whoever to do it for me. But the idea behind observability is to check how your entire system is operating. It's not, it goes deeper than just monitoring, which checks if your TCP port or whatever other solution is opened. It's going to report metrics that allows you to analyze how well your system is operating. In short, what is going on. Yeah, let's go. So why do we want to use the load balancer in our observability question? So the load balancer is strategically positioned in your infrastructure. So usually you have heard already about north-south or east-west. And so when you do north-south, the load balancer will be the first device that your client traffic will hit before going into your application. And then when you are doing east-west, this will be the load balancer that will be between your services when they need to speak to each other. Or even to speak to the database or to whatever other system you have behind your infrastructure. So they are positioned between different type of clients. They work either at network or application level, which means that they can collect a lot of information on what is actually going on. Usually, when you have a microservice infrastructure or when even you are on internet and you need to operate with lowest possible latency, which is key now to make business on internet. If you are too slow, people will switch to another system. You need to trust your load balancer, and this is important, and that's why HAProxy is popular for 25 years. For those who don't know HAProxy at all, whenever you do a Git pull, you're speaking to an HAProxy. When your kids are playing Roblox, they are using an HAProxy. Whenever you browse an ad on internet, it's mostly an HAProxy. Or whenever you make a payment somewhere, there is an HAProxy as well. It's everywhere. Something important that I'm going to leverage a lot here today will be the logs. So logs, HAProxy will generate logs about what's happening, and then we are going to see how we can leverage the information and try to figure out answers to questions I'm sure you already had in every infrastructure you guys are managing. First, HAProxy is a reverse proxy. So reverse proxy means we cut the TCP connection. So you have two TCP connections, one connection with the client, one connection with the server. It's two different connections, which means that it's easy for us to speak IPv6, TLS 1.3, HTTP 2, HTTP whatever you want with the client. And on the other side, with a server, expose a weak SSL v3, IPv4, whatever you want. There is no transformation of the packet. There is one connection which is closed by the kernel, or maintained by the kernel, sorry. And HAProxy will open another connection to speak to the server. So there is no NAT, even if that's the same effect. But this way, and that's important, HAProxy will not see any packet. Packet will arrive in the kernel will aggregate the packet into a buffer of data, and HAProxy will have access to this buffer of data. And in this buffer of data, it can process TLS, HTTP, or whatever else you can put in there. And because of this, we can easily make a lot of metrics on every URL, everything which are passing through. So we are, of course, advertising that you should use a load balancer for your monitoring and observability, but definitely you can use anything you have in your infrastructure. Sometimes some traffic does not pass through the load balancer, or sometimes for some database protocol, for example, we don't have access to the payload. So it's complicated to say when you did this select, it took 20 milliseconds. And when you do this other select, it took 10 seconds. So that's why you need to have other type of monitoring and observability system in your infrastructure. We support as well OpenTelemetry and Prometheus with HAProxy. So OpenTelemetry will happen in the next release in a few weeks. There are so what can we see with the load balancer? As we've seen, as we explained, because we manage the network connection, we can see network failure. We can see retransmit. We can see latencies. We can see timeouts. You know, the famous, I always love this question or this feedback from customers. I have a problem with timeout. No, the timeout is a solution. It's not the problem. The problem is something else in your application, and HAProxy protected your services from crashing because they would pile up sessions if you don't have any timeouts. Delays, etc. All of this, you know, furthermore, when you run Kubernetes on VM, on bare metal, you have so many layers of abstraction that the network become obscure. And even if you take a TCP dump, it will be complicated to figure out what is really happening. And that's the role of the logs that we can produce for you to have access to all this information without even running on a TCP dump on the machine. Yeah, we can see some other stuff. So bandwidth limitation, sometimes that's quite complicated to figure out, but we have some metrics for this. We can see down to per URL or even per whatever you want to collect. So if you have an API which is /v1/basket and query string with a basket ID, for example, we can have metrics on this basket ID, for example. So we can log everything. And if you want to know the latency based on product in the basket or whatever, we can have all the metrics. It's very powerful. You can figure out latency per application server. So that's what we call a node, per type of clusters, etc., etc. Okay, so now if I want to introduce quickly HAProxy, so for those who don't know and for those who know, this is a famous stats page of HAProxy. I mean, it was developed in 2001 and still beautiful today. Yeah, maybe, but so you see this in this spreadsheet or table, you have a lot of metrics that can definitely help you. Below, we also have a log line of HAProxy. So most of the time, people are scared to read the log line because you have a lot of characters, a lot of things, numbers, some weird letters, SD, NN, etc. But this is goldmine. And I'm going to explain you how this will save your life. That's why we are here. So HAProxy will expose metrics using logs. We've said it already. When you guys are using microservices and HAProxy is the first layer in your infrastructure, you definitely want it to set up the unique ID that all your services can log and populate, so you can have your drop down of latency for each service. We are going to expose statistics. So you've seen the nice stats page. Be aware that this stats page also can be exposed using CSV and JSON. We are modern. Or whatever other format you would need. We have a lot of wrappers that can read from it and expose it into other format. We have stick tables in HAProxy. So stick tables are named for stickiness, of course, when we want to ensure that the traffic from a specific user always go to the same server. Otherwise, I need to login effect, and because the traffic is balanced to every server in round robin, then you will never get logged. That's because your application misbehaved, by the way. But definitely, so stickiness is here for applications that needs it, sorry. But definitely, we can use stick tables as well to monitor your traffic. So in live, instead of having the traffic in logs and compute logs and grep and count and WC pipe WC-L, etc., you can use the stick tables and say, I want to track source IP if they hit this URL and I want to count number of errors or requests per second, etc., etc. That's very powerful. We use it a lot. So we use it here in the frame of observability, but we use it a lot as well to detect abusers. We spoke about fraud detection before. We can use this in that case. People that are you want to enforce rate limiting, etc. That's exactly the same use case. Something we added recently in HAProxy, it's something we call the traces. The purpose is to see exactly what is happening at the protocol level. So it's more for debugging, troubleshooting in HAProxy itself. But it's very interesting when you enable it to have a look at what the client exactly sent, why HAProxy accept or deny the connection, etc. What was wrong in the client or in the server, and have a look at it. And that's easy. It's like a TCP dump, but running in HAProxy traffic processing. So I'm not going to go deep dive into explaining you all the details of what's happening between the client, the server, and HAProxy in the middle. The most important is that we have something we call timers and events in HAProxy. And as soon as the connection has been accepted, you will have TH, and then TI, and then TQ, etc. I'm not going to go into the details because I just have 25 minutes. But be aware that all these timers can be logged. I think we log by default 5, and you can enrich your log line to get more. But with this, it's easy to spot if you have a problem on the client side or on the server side, or even on HAProxy itself, because we can log also the time HAProxy took to process the request. So we are not going to blame others. We can also blame ourselves. So event timing. So we have a quick zoom on the stats page where you see the various timings of the time the request was in queue, the time to connect from a TCP point of view to the server. The response time is how long it took for the server to generate the response. And the total time, which is how long it took for HAProxy to read the response from the server, stream it to the client, until the client said, okay, I fully received the request. Or the response, sorry. Each of these timers will appear in every log line for every request sent to any server. So you have vision on everything. We have a tool called HAlog that you can use. So the guy who answered, I use grep on log file was me. And HAlog is kind of a very powerful and fast tool to analyze all these log lines. Each timer can have also a timeout. So when I said sooner, timeout is not the problem, it's the solution. You could say, I don't want HAProxy to wait more than 2 seconds when it connects to a server. I mean, on a local network, SYN/SYNAC should take less than 1 millisecond. So 2 seconds, we already allow one retransmit, which is more than enough. If you don't have any answer from this server, you can consider it dead, and you can tell HAProxy, try the request on another server. So you can hide the problem on the client side. Client will just get higher latency. What else? Oh, yes. Something very important that I'm going to highlight later during the demo is the blue code. So the timers are in red, and we have the blue code, SD in that case. So that's something we call the termination codes. Termination code will tell you first if there was a problem or not. If there is no problem, it's fine. If there is a problem, it will tell you if the problem was on the client side or on the server side during the connection, establishment of the connection, so TCP layer, during the processing of the HTTP request, response, headers, data phase, etc., etc. So you will know exactly what happened when the failure happens. I'm not going to go over the cookie here. It's not part of the problem. That's exactly what I said about the termination code. We also have a HLog that can help you sort this and filter this. And I think what is this? Yeah, we don't mind. I think demo. Oops, I will come back to the dashboard after. So, is this big enough? Can you guys read? Or you will have to trust me. So that's a quick, sorry. Okay, so that's a quick demo. First, I wanted to send normal request. So in normal request, you will see, so that's the entry point in HAProxy, the backend that was used, the server that was selected. We have nice round robin. Then we have the famous timer that we can come back later on. This is the status code response from the server, 200. And we see the termination status is --. No problem. Now we have a bad guy doing a slow loris attack. So slow loris is when you open a TCP connection and then you send the HTTP request very slowly. So in that case, my client is sending 1 byte per second. In my HAProxy configuration, I said, okay, I let 5 seconds to the server to send, to the client, sorry, to send the HTTP request. Usually when you have SYN/SYNAC, sent by the client, the request will arrive very fast after. So it's usually a few milliseconds. Now, if I have a look at my log line, I will still see my HTTP front, which is the front end. Then I don't have any backend name. The backend name is the same as the front end, which means that the request stayed in the front end. It was not routed to any backend. No server has been selected. I don't have any timers. Why? Because after 5 seconds and 2 milliseconds, HAProxy decided that this client is too slow to send an HTTP request. Then HAProxy decided to return a 408. Now, status code is C lowercase. C like client, easy. R like request. So there was a timeout problem with the client when he was sending the request. That's very straightforward. Then I asked my client to send an invalid request. So basically the client is sending HTTP instead of HTTP, which is not RFC compliant. HAProxy will deny the request. Once again, the request arrived in the front end and HAProxy returned a 400, not valid from a protocol point of view. And then we have 2 new code. So P for proxy, that's the proxy which took the decision to stop the request because the client sent a request which is not valid from a protocol point of view. Now we have a farm with 4 servers, and people on Twitter are complaining that something is slow on this application. So your sysadmin will have a look at the logs of HAProxy, and that's very simple. You have all your servers here. All of them seems to answer pretty fast. So the response time of the server is this timer. And then at some point, oh, server 1 takes 2 seconds to reply. So sysadmin, if you have a problem, first you go on your load balancer, you disable server 1, so operation can continue as usual. Have a look at your server, maybe backup is running, antivirus is running, I don't know, whatever. And then you can fix the problem. So you don't have to look everywhere, dig into gigs of logs, etc. HAProxy will have the answer for you. Another test. So in that case, it's kind of the same. So we have various URLs / foobar, and when we have a look at the logs, we say, oh, foobar is much slower than /, and any server is slow on foobar. So it's not a server problem anymore. It's clearly an application problem or a database problem behind this application. So you can wake up the developer and they can have a look. Yes. So this one is interesting. So in that case, HAProxy received a request. The request was forwarded to the servers. And the server just closed the connection. And so S uppercase, it means that it's on the server side. That's easy. And H means that HAProxy was sending the headers and the server closed the connection. In that case, HAProxy will return a 502 to the client. So you're lucky, HAProxy can do a retry. So I did not enable it in the configuration, but for example, you could say to HAProxy, oh, if a server crashed in the middle of the request or the response, then select another server, failover, continue as usual. But you can easily see that in that case, so I just enable an error on every request, but that's easy to see that the problem in that case was on the server side. Then we have kind of the same, but you see in that case, HAProxy has returned a 200. Actually, the server received the request, but the server crashed during the data phase. So the server has processed the request. The server was streaming the response, and in the middle of the streaming, it just stopped for some reason and sent a TCP reset to HAProxy. So we still have a 200. It's not an error because the server has fully received the request, started generating the response. The response was a 200, but at some point, we don't know why, server crashed. So it's easy to spot any error. And furthermore, when you guys are, as I said sooner, on Kubernetes, on top of VMs, on the public cloud, etc., where you can't trust anything below your application, when you have these log lines, it's easy to spot or to go to Amazon or to go to your Kubernetes provider and say, hey, my HAProxy said the problem is on this side. Please help. And that's same as before. So in that case, the server just returned something which is not HTTP. So instead of returning HTTP 1.1 200 OK, it says HTTP with 1P two more. And same HAProxy says, I read the response, but the proxy said the response is not HTTP. So I had to return a 502 to the client. And that's the end of the demo. As I said sooner, we have an enterprise behind HAProxy. All of this, everything I showed you, is open source. You can install HAProxy tonight or tomorrow and start playing with that, start enabling this. You will have to make your own dashboard, etc. But in enterprise, we have a control plane that used to manage your fleet of HAProxy. And of course, we are going to collect all the metrics so we can make nice bandwidth, connection, etc. dashboards. We can have, that's the same type of thing with number of requests, etc. We have something we call a request explorer, which is kind of a grep on the log. So you can easily say, show me all the response that took more than 2 seconds. So you will just have them and you can click. And when you click, you can have a deep dive and you see all the timers we have, how long it took for the client to send the request, how long it took for HAProxy to process it, how long it took to send to the server and the server to reply. In such case, everything happens pretty fast. But if you have a slowness, it's easy to spot and it's easy to filter. The role of the enterprise is to make it easy for you to consume versus what you have in community and grep and tools like this. We spoke a bit sooner about, during the survey about Datadog and SIEM, other SIEM system. HAProxy as open source solution, of course, is well integrated with all these solutions. All of them have dashboards, metrics that can leverage all these information that HAProxy can provide you. A quick conclusion. First, choose the right load balancer, of course. Most of you or some of you might have multi-cloud or, having to run on Amazon and stuff like that, and you have to trust what they provide you. The advantage of using a third-party neutral solution is that you can show them if they have a problem and say, okay, my load balancer says Cincinnati take 100 milliseconds in the same AZ. Doesn't make sense. So the problem is on your network, stuff like that. You need to exploit your stats, of course, that's important. Enable the logs on HAProxy if you haven't. The default log line you've seen, I would say today is very obsolete. It's the default one, but you can enrich it with anything you want, literally anything. You can capture everything from TLS protocol. You can capture everything from the payload, the JSON payload, etc. If a user agent is important, you can log it, all this kind of thing. And I think that's mostly it. Yeah, the idea once again with when you have HAProxy is to detect anomalies before they happen. So because we are logging all these timers, it's easy to make graphs like the precedent speaker explained, where you can start seeing the tendencies and the percentile, and that's easy to figure out what will go wrong very soon. And I think that's last slide.
All right, so if you want to submit any questions, you can type them into here, or you can also just shout and I'll give you the microphone as well.
I hope. It's easy. Okay. Oh, yeah, does HAProxy support Kubernetes Gateway API? Tough question. So we're in the middle of it. There is a KubeCon, so I can't say more, but it's coming. So we released something we called HAProxy Unified Gateway in December. It does not support all the gateway APIs yet. That's why it was released in 0.5 or 6, I think. But v1.0 will be announced soon.
Okay, next question. In globally distributed, these are coming in. In globally distributed deployments, how do you separate latency caused by cross-region routing from backend application issues using HAProxy metrics alone?
That's a good question. I would say, so depending on the way your configuration would be architect, you would have either servers or backends pointing to different AZs. And then usually we name the backend with the AZ name or stuff like that. We put labels on the servers. So it's easy to split the stats based on this and then figure out whether the problem comes from AZA, AZB, etc. Also, I think HAProxy can report now information it can pull from the kernel level, from the socket itself. So the metrics such as packet loss, retransmits, etc. So that's easy to log them and to make new graphs. And then you can correlate based on the AZ name and the packet loss, etc., and make some graphs on top of this.
Okay. Does HAProxy let me copy headers from the first TCP header into the second?
So no. So I guess this is because of the what the name reverse proxy mode. It's totally two different TCP connections, and it's up to the kernel to decide. I don't think we have any feature in HAProxy which allows you to set TCP headers. We could do this with HTTP, of course, but at TCP, I think no, not yet. But that's something we can maybe have a look at.
Okay, in microservices environments, we often have metrics from HAProxy, Prometheus, and tracing systems like OpenTelemetry. How do teams effectively correlate HAProxy's request timing metrics with app-level metrics to quickly pinpoint where, like the service or the database, the latency is introduced?
Yeah, that's the role of the unique ID that we can log. Because when you create the unique ID at the very first layer, then every service is supposed to log it as well. So even if you're not using HAProxy on the east-west, for example, all the services should log this, and then you can correlate using this unique ID. If HAProxy is used on the first layer and then you use something else, HAProxy can only report the global latency, but then you will have to have a drop-down per service. So if you use HAProxy everywhere, you will have it. But if you use Istio or the like, they also have the same solution. As long as we have a common unique ID, it's easy to correlate. So,
okay, one more question. Will HAProxy become a single point of failure?
that's the best question. It is. And that's why you want to have HA, high availability. That's the name of the solution. So you have two options. Either you need low to moderate traffic, and by moderate, I mean a few 100,000 per server. Then you can have active passive. And if you are a GitHub or a Roblox, then definitely you have literally millions of queries per second. So you want to scale out. So usually what people do in that case is that they will have a fleet of HAProxy servers using BGP and what we call ECMP on the BGP routers to load balance the load balancers. And that's how you scale, basically.
Okay, fantastic. Thank you very much. I know there's a few extra questions, but please, you can send those to Baptiste during the break. Before we go to the break, Aerospike has the raffle winner for the Game Boy. It's Raj Shekhar Bhardwaj. Raj? Okay, nice. Congrats. You can collect it from the Aerospike folks over there. Okay, we will be back again in 15 minutes. Thank you.
So my name's Alam. I put the A in AI and A in annoying. I'm joking. So I'm going to be talking about eBPF. I know most of you guys say you don't know what it is. That's fine. Neither do I. Okay. So can we do? Can you? Okay. Oh, that's off. Tech support. I need help. I need help. Hey, this is my Facebook. Okay. Just a second. Wait, I do. There you are. Present alert. You good? Okay. So this has happened before. And okay, it's happening again. Make it better. Is it working now? Okay. We finally got there. Okay. I'm gonna be talking about eBPF. Yeah. First, Slido. So can you guys scan that? It's pretty much a reiteration of what we did earlier on. Come on. One pen. That's the best type. Flying blind. Prayer sometimes work, can be breakthrough. Tech cards never answer. Full spectrum that's shown off. Okay. Let's have that. Logs and prayer. Okay, we need to talk about religion after this. That's very interesting. Very few people are using data-driven. Flying blind. That's very much my motto to life. Okay. Okay, cool. Work. Okay, me. Oh, not me. Not me. That's me. Okay. So a little bit about me, because it's always about me. So 4 years in tech. This is my third talk. First one was in Elastic, in London, then in Yorkshire DevOps, security as code. Contribute to AI, cloud custodian, and York. Mainly didn't come in for my jobs. Certificates, tech support, certificates, Cilium 5, Linux Foundation, I got 7 from them, AWS 10. I did all the free badges, and if I sorry for me, so they let me be a cloud community builder, mainly focusing on security. Cisco 16, platform engineering 4, and Chain Guard 2. I did all the free stuff. I just got bored. I need a social life. Someone help. Okay, so today we're going. It's going to be focused on 5 parts: the current environment, eBPF, the CNCF ecosystem, building security observability patterns. So that's going to be a live demo, pre-recorded demo. I then integrate it into real world and give examples of companies that use it. Okay. So cloud native security crisis. Obviously, I had to put crisis on there because, you know, marketing. Sorry, marketing. So I'm going to give you a rough overview of the landscape at the moment. Okay, 67% of companies deploy or delay or slow down applications due to Kubernetes security concerns, according to Red Hat. I was speaking to my the head of infrastructure the other day, and he said to me, very few companies actually provide it as a commercial offering. It's more like built in-house. 95% of organizations, they delay workloads or delay cloud native builds, mainly due to security, mainly due to the current security vendors out there. They're very agnostic, or they're very like vendor focused. The disconnect is security blocks innovation. Blind spots called leakages, compliance challenges. Okay. The traditional approach, dynamic versus static. We live in a world where everything is changing. So you've got stuff like AI, never heard of it. Containers are spinning up, spinning down. IP addresses are changing. Microservices communicate empirically. Traditional tools assume a static IP, persistent host, predictable network boundaries, allow all a block wall. Geo-blocking, cannot track or rapidly change workloads. Distributed and centralized, cloud native, thousands of microservices are spin up and spin down. Nodes are currently being deployed. The traditional tools, monolithic applications, so with clear perimeters, cannot change and request across distributed systems. You guys can read that. So basically, what it is, I'm going to sum this up to you. The world, technology is dynamic. It's not static. It's static because users' behavior changes. Management is always saying that we've got this customer who's still, they want this, and then applications need to fit into it. So you're not working with one application, you often work with multiple applications. Okay, so eBPF. Started less than 10 years ago, I think, is a technology built within the kernel. So a lot of the organizations, a lot of the infrastructure alerts, they come in at CPU level, or they come in saying that so-and-so is down, but they don't really focus on the kernel itself. It don't really focus on the host. So what it does, what eBPF does is that it's based in a safe sandbox. It's restricted to a virtual machine. It's kernel level execution. It's container aware, so it's aware of C groups. It's aware of Kubernetes. It's aware of Docker. You don't have to turn on and off the application for it to work. And that one. We already did that. Okay, so how does it work? So it's written in a language similar to C. It's compiled with an LLVM compiler. It's verified, and then attaches to an execution. So it's basically a Linux level. The verify ensures that it doesn't crash the system. And then key value data structures for storing stats ensures that data is between eBPF programs, user spaces, and attaches to a point. Okay, so the past two talks primarily were focusing around resource allocation. Traditional resources are clunky. They're always changing. eBPF, less than 1%. Latency impact is minimal. Memory usage, low. Facebook shows that eBPF-based monitoring solutions up 10x performance improvements over traditional space methods. It's no content switching, runs entirely in the kernel. JIT compiles bytecode compared to a native machine code load time, event driven. So it's more proactive than reactive. Okay, it's perfect for CI/CD deployments. Zero no code changes, no sidecards, no agents to inject. My previous place had to install agents onto individual hosts, which is a pain in the backside. It understands C groups, namespaces, and Kubernetes metadata by design. So no manual mapping to IP addresses, complete lifestyle visibility. Okay, so the ecosystem. Cilium, which is recently was, I think Cisco, I said some really nice stuff about it, is provide network observability and security and replaces IP tables with high performance kernel level packet processing, Tetragon, kernel native security enforcement, applying policies directly in eBPF, dramatically reducing events to user spaces, Falcon, runtime security, and Pixie, zero instrument observability for Kubernetes. There's also like 41 other projects. Some of them are graduated and some of them have not. Falcon, for example, runtime threat detection. It's a graduated project for detecting unexpected behavior for potential threats in real time. Originally created by SysDig, is now used in production by organizations worldwide. Real-time detection, customized rules. It's lightweight, it's extendable rules. The container escapes, attempts to break out of container boundaries. So crypto jacking, unauthorized crypto mining processes. Anybody doing this, please let me know. Privilege escalation, attempts to gain, evaluate permissions and data exploitation, suspicion files, and network activities. Okay, then Telegram is a Cilium subs project that applies policies and filters directly into the kernel with the unique approach dynamically reduces the number of events sent to the user spaces. Key differentiation between Falcon and Tetragon filters the kernel, enable massive performance gains. Again, resource allocation. A lot of these, what they do is that they're conscious about resources. Falcon approach collects all kernel events, sends to user data. See? Okay. So what I did was that I find 4 main themes or security approaches that happen, and then brought script, and then did a live recording on my own device. But the main focus was around answering several questions that I've seen in production. Every process, so process execution and monitoring with compliant context before user spaces. Okay, so what runs and where, how it was launched, who launched it. Just like basic questions, but it allows you to see what's actually happening. Where did it start? Where did incident start? Is active. Every process is actually captured within the kernel. Like I said, it's at kernel level. It's not. But yeah. So here's one of the live demos. Can everybody see this? No. Okay. See. There's your process ID. There's container. There's executed. And then there's time stamp. So you pretty much have enough information just to see what's happening, where it's happening, and where and who did it. Okay. Network security correlation answers 3 critical questions. which container, what process, and real-time correlation. So, and then we got demo. You got script on one side, then you've got the actual application on the other side. See, you got TCP connection, you got a PID, and you got the process. Okay, file integrity and monitoring reveals critical contents that traditional file system logs cannot provide. Who executed them, which container performed the access, and whether it was authorized. So you got the timestamp. Okay. This is all at a kernel level. eBPF, like I mentioned before, it's very lightweight. Then system code for profiling, anomaly detection. It detects anomalous behavior, baseline container behavior, identify potential container breakout attempts through suspicious syscall combinations, real-time syscall frequencies, arguments, and calls containers within containers. And the last time demo. H4 probes system called profile started profiling system usage and detect anomalies. And okay, integrating into, we're almost there. Integrating into real world impact. So the thing with CNCF ecosystem is that you don't use Grafana by itself, you often combine it with something else. So this is Prometheus and Grafana combined. You got infrastructure metrics, CPU, memory, network throughput, and latency. And here you got low-key and you got elastic, suspicious calls, file access events, and network connections. Companies that use eBPF at the moment, Meta for pretty much all of their packets. You've got Google, Android, and you got Cloudflare. Traditional versus eBPF. Traditional is reactive. Something happens, then you react to it. Log-based analysis, nobody likes doing grips. Nobody does. High overhead, often costly also. Limited visibility, content switching. It's real-time detection, kernel level visibility, minimum overhead, and complete content kernel space execution. And the future of cloud native security. A lot, yeah, that's about it. They want to connect to me. Just petrifying. That's it. Fine.
All right, thank you very much. Okay, hold on a moment. Wait. Just in case there's any questions that come up. Gee, this is
more of a compliment. One of my slides, I showed that you got Prometheus and you got Grafana. You've got low-key and you got elastic. They both can work hand in hand. You don't have to be focused on one application. Their website has a lot of good projects you can do. I have no idea. Not a question. Not a question. Another question, okay.
Okay. Okay, let's call it a night then. Thank you very much, everybody, for coming. This concludes our evening. We're going to be back again here on the first Wednesday of every month, so whatever next month is. There is a pub nearby called the London Pub. If you would like to keep chatting, we'll all just congregate and go over to the London Pub together. Other than that, thank you so much. Have a lovely evening.